Good afternoon and welcome to Lecture 23 in MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and welcome. Make sure that, again, you can hear me okay. Hopefully the audio is coming through clear. And in today's lecture, we're going to go over vertical and horizontal asymptotes. Asymptotes. There we go. Excellent. Good. Thank you for saying that in the chat. And I'll also keep an eye on making sure that the video is keeping up. So just as a reminder, we have a quiz tomorrow. And it'll cover what we had on assignment 8. There was questions about marginal functions in economics. I've posted the solutions to the algebraic skills and limits. And as well as we had some questions about derivatives. We had questions about doing the limits, doing some algebraic manipulations of it to get to the limit answer. And we also had questions about using the definition of the derivative as well. Why, again, is it so important that we were going over about this was this relies, or this uses, limits. And what ends up happening is for this ends up leading to curve sketching. So what that means is without doing a lot of calculations like a table of values, we can actually sketch curves based on some of the facts that we can derive using calculus. So, and make sure that I keep an eye on the chat. Excellent. Okay, and it looks to be a small class today. So again, if there's any questions as I go through this, make sure that you ask them in or stop me. So the first thing again, what we're going to do is we're going to sketch the function. Oops. What we're going to do is sketch that function, 1 over x squared. So I could sketch that, or what I'm going to do is quickly show you just over here. So here's a graph of 1 over x squared, and we see again, it's kind of smooth. It doesn't quite touch there. Goes up to infinity around x equals 0, and same thing on the right-hand side. So again, I can see what the limit is going to be like. So again, we are going to explore so we've kind of sketched that. So what we can actually do is something like this. There we go. And we also are interested in kind of what's interesting about this is around x equals 0. So what is the limit of 1 over x squared as x goes to 0? So we can use a table of values. And we can actually see kind of what it's doing as it's going from the left-hand side. And we'll also look at what it's doing as it's approaching from, sorry, there's the left-hand side and this is the right-hand side. Okay. So I have my LibreOffice spreadsheet open. So again, over on this side, I will do the calculation. Oops, it should be A2. There we go. So at the function at x equals 2, it's a quarter. If it's at 1, it's going up to 1. If it's going up to, getting closer to 0 again. So we have around here. So I have it around -1/2. So it's around there. It should be around. There we go. There we go. Around 4. Good. Same thing. I can drag this down. I got 400. It's going to 10,000. I'm getting, that's quite high. Let's see, how many zeros are there? I've lost count. It's a really large number. So again, as it's getting really closer to 0 on the left-hand side, it's getting to be a really large number. So it's growing without bound. So when that happens, it is going to infinity. And it's positive infinity. And the same thing happens when I look at the right-hand side again. I'm just going to just drag this on. Won't worry about that divided by 0. But again, as I go from the right-hand side, it's getting bigger and bigger and bigger and bigger as well. So we also say that this is infinity. Now, it's okay to write this. It's okay to write, but it's also important to know that this limit is not a finite number. It's not a finite number, because again, that's just a symbol. That means infinity. And it's not a finite number. So again, that also means that that limit does not exist. Now, we've seen, okay, so why is this so important for us? We have this function, 1 over x squared, and we see that it's going off to infinity at around x equals 0. And so I'll make a note here. So it's the function f has an infinite discontinuity. Again, it's not defined at x equals 0. So f has an infinite discontinuity at x equals 0. And we also say, so that's kind of like the algebraic understanding of it. And we also say, that line, so this is kind of the graphical interpretation. So the line x equals 0 is a vertical asymptote. Of 1 over x squared. So again, vertical asymptote. So sometimes you'll see people kind of just draw it like a dotted line or a thin line or something like that. There's my y and x axis, and so you'll kind of see that it does something like this, and it never actually touches it. It kind of goes off to infinity. So some people kind of put a half arrow kind of like that, and another arrow on that side. There's kind of my sketch. And so that's the vertical asymptote. Okay, oops. So we had an example where we had the limit was defined for infinity. Well, not defined, is infinity. So let me just give you two examples. And maybe I'll use a different color. Use orange here. So we'll say like right here. And right here. So again, these are just my examples. So I'll say here is my x, it's equals to x naught, and x is equal to x naught here. And so if I have a limit as x goes to x naught of f of x, and we say that is infinity, what that says is then at that x naught, it goes up on the left-hand side, and it also goes up on the right-hand side. And similarly, if I look at this function, and I say that it's going to negative infinity, what that means is it's going off to negative infinity on the left-hand side, and it's going to negative infinity on the right-hand side. So while it's not defined, when we write this kind of shorthand form of it, saying that it's equal to infinity, it's going to infinity on the left-hand side and the right-hand side. And in this case, it's going up. So this is for positive infinity. And then it goes down. Both of them together on both sides is going to negative infinity on this in this case. Okay. Oops. Let's grab another sheet. Okay, so let's just jump to an example. We have our example here, and we have the function y equals x over x squared minus x minus 6. And so, you know, part A would say, like, find the vertical asymptotes. And then part B would be, you know, sketch the graph. Near the asymptotes. Okay. So it's always good why we keep going over the same kind of algebraic or concepts over and over again. We kind of expect that there's a discontinuity, an infinite discontinuity, when the denominator is equal to 0. And when is that equal to 0? Well, that's when this denominator is equal to 0. Which means then that I could factor this. So I get x, and x, my two numbers, I need to have a number that multiplies to give me -6 and it adds to give me -1. And those two numbers I can think of is -3 and +2, which then means that my candidates for my asymptotes are at x equals 3 and x equals -2. These are my candidates for being a vertical asymptote. Is that sketch? Yes, sketch the graph near the asymptotes. We're going to sketch it near the asymptotes. Doesn't have to be extremely accurate at that point, but you'll kind of know what the behavior looks like. So what we do is we have our one candidate, we have our second candidate. So what we'll do is we'll look on the right-hand side of this. So what you can think of is you think of a number, say think of a number that's near on the right-hand side of it. So we'll say like think of 3.01. Okay. So what does that mean? Okay, so I have, if I put that here, the 3.01 here, that's a positive number. If I put it in here, that's 3.01, so that's -3, so it's like 0.01. So that's a fairly small positive number. And same thing over here. This is still kind of a positive, so like 3, so it's like 1. Okay, so I have a positive and a positive. Those kind of, cancel out to give me 1. But I have a very small positive in the denominator. And because it's a small number, means that it's growing quite large. So that means I have a large positive value. And again, so as this gets closer and closer to 3, this is going to get larger and larger and larger, which means that it's tending to infinity. So that means that this is equal to infinity. Okay, so then if I think of x going to 3 minus, so it's from the left-hand side, and I have x of x minus 3 and x plus 2, and we'll say think of 2.99. So what we get there is I'll have 2.99 at the top, so that's a positive number, over 2.99 minus 3, that's a small negative number. And then over on this side at 2.99 plus 2, that gives me a positive number. So just thinking about that, I have a positive and positive, so that kind of gives me 1. But I have a really small negative number here. So again, 1 over a really small number makes it a really large number. And because it's negative here, I have a large negative value. Which means then that it's tending to go to minus infinity. Okay. So for number 2, we'll have the same idea. We have it going to, from the right-hand side, my function there. And same idea again. You just apply the same, -2. And the same thing happens again. So this becomes infinity. And same idea for this one. -2 going from the left-hand side. And so you do the same idea again for this as well. And that makes it a minus infinity. And this is where we get to the part. So this is part A, part B. So we're asked to sketch. Again, really rough sketch. I mean, I wouldn't start reading values off of this sketch. That's how sketchy it is. So I have a -2, and then I'll have like a +3 on this side. Okay, so then from the right-hand side, it's going off to infinity. And see, it's really small. I don't have to sketch the whole function. Okay, and then around from the -3, so sorry, 3 minus, so that means that it's coming from the left-hand side, and that's minus infinity. So it's going that way. And at -2, I'm going on the, from the right-hand side, it's going off to infinity. And from the left-hand side, it's going down like that. So that's kind of my quick sketch. I don't really know what's going on in the middle of this, but we would also get to use some later ideas that we've learned previously, like our concavity, where it crosses the x-axis, where there's a min and max. We get to use more of those concepts later to kind of refine our sketch. So that's what a vertical asymptote is. It's wherever the function itself has a infinite discontinuity, and there's kind of like a line that it's approaching, a vertical line it's approaching, and it never actually gets to it. So it's going off to infinity, whether it's infinity in the positive direction or negative infinity. Number 3. Now we get into what are horizontal asymptotes. So if it was a function that was approaching it for a vertical asymptote, it's a line that it's approaching in a vertical direction, and it's not quite touching it. It's going to be it's very similar for a horizontal asymptote. It's a line, a horizontal line, that the function is approaching but never touches. So, for instance, we could look at the example. Okay, and what I'm going to do is switch over to using some technology. Instead of using the 1/x, I'll use x squared plus 2, and it's going to be divided by, of course, this is just my title. There we go. X squared plus 1. There we go. And this is going to be what I put in my formula here. So I'll use this, and I'm going to square it, plus 2 divided by this function squared plus 1. And what I'm going to do is I'm going to not just use that. Getting really large values. And I'll take this and I will drag it. That is interesting, which means the computer is having a round off error. So at some point, we've gotten the number so large that it actually equals 1. It shouldn't equal 1. It should be getting really close to it. Same idea if you want to plot this, divided by x squared plus 1. So we look at the graph using Google. So there we go. And again, we have a kind of like a bell-like shape function. And what we see here is that the function is coming down. And as we go out to positive infinity in the x direction, you can look at the value up top here for this y. And as we're getting further out, it's getting really close to 1. Now, so that's what we'll do. We'll also make a note of this on ours. So what we saw was that we have our function x and f of x. And what we noticed was, say, if we had 1, we had 1.1, we had 2, 1.2, and we got down to 1,000. We got close to 1.000001. So the limit of that function, so the limit as x goes to infinity, the positive infinity, x squared plus 2 over x squared plus 1 is equal to, it looks like it's equal to 1. Now we've done this with values, we've done it looking at the graph, but hang on, we will show you how to do this algebraically as well. So let's also look similarly. The limit as x goes to minus infinity. Okay, so again, I'll switch back to here, and instead, minus 1, minus 2, minus 3, minus 10, minus 1,000. Maybe I should just put a minus there, and a minus here as well. Same thing happens. So it doesn't change. I mean, I changed the values, and so this propagated through. So it's the same idea. You also see that it's symmetric. It's symmetric about x equals 0. So again, in the negative values of x, as we're going to negative infinity, the value is getting, so again, you can watch over in that y value over here, that y value is also going towards 1. So again, you can do a table again like that, but the limit as x goes to negative infinity is 1. So what that is, and what I'll do is I'll even draw it, just give a little sketch. And kind of here's my equals 1. So that's y equals 1. Here's my x. And so it kind of does something around 2. So there's my point 2 here. And it goes like that. Okay. So in this case, y equals 1 is a horizontal asymptote. So we'll give it a little bit of a better definition. So let's do this a little formally. So we'll say that the line of y equals L is a horizontal asymptote of the function y equals f of x if either the limit as x goes to infinity, the positive infinity, if that's equal to L. So again, like this, just going back to our original idea, which was we had the limit going to infinity, there's our function, and it's equaling 1, so there's our L. And so that would correspond to y equals L, or y equals 1 right here. So that's our horizontal asymptote. Or so you'll have to check negative infinity as well. Now there's many ways to approach a horizontal asymptote. Again, it can do some weird stuff, but as it's going out to infinity, it starts to approach that line. So what I mean is for instance, I have 4 cases that I'm going to kind of, or 4, let's say, examples. Just drawing my axes here. Okay. So, sorry. It's a habit to have to label all my axes. There we go. So, I'll keep the color consistent. Maybe I'll keep using orange. So we'll have some kind of horizontal asymptote, and this is going to be our L. So there's y equals L right here. And in this case, we'll say that the limit as x is going to infinity is equal to L. So in this case, it could look something like this. It can actually cross the horizontal asymptote in the beginning at some point here. But again, it's the long-term behavior that we're interested in. So again, it approaches L. Something like that. Okay, maybe I'll extend this a little better. So what I could do on this one right here, I'm going to say that, again, here's another example of it going to positive infinity over this side. So I could do something like this. Could do something like that, getting really close to it, so it's approaching it from the other, the bottom side of it. Oh yeah, you could do something weird like this. So here's my y equals L. And again, looking at the infinity. So this is kind of a weird one because it'll kind of do this. It could do something like this, oscillate back and forth. And it'll gradually get closer and closer to L. And, oh yeah, and we should also maybe give a negative infinity looking one. So the limit as x goes to negative infinity, which equals L. And I could do something, you know, it doesn't really matter. It could cross here, like this, and here. And then at some point, it has to kind of approach it. Something like that. I gotta be careful with that, because that kind of looks like a vertical asymptote there, but yeah. You know, it can do lots of weird stuff. A horizontal asymptote. Okay. What's another one that we could do? And this is number 4. So again, there's my y equals L here, y equals L. So in this case, we'll again look at an asymptote as it's going in the negative infinity. So again, it could come up, approach it as well. Something like that. Oops, gotta be careful. There we go. I don't know. And it could do some weird stuff before that. Something like that. Oh, and so another thing, you could actually have, you don't necessarily have just one asymptote. Somebody might ask, what does it look like when there's 2? So here is 2. I have y equals L. We'll use capital M here. And we'll say that it's the limit as x goes to minus infinity. So as it's going to go to minus infinity, it's going to approach this asymptote, this L1. Let's say L, and here's another limit. It's M. Okay, so for this case, it needs to approach it. So what I can do here is I could say, oh, gonna cross it and then come back and slowly approach it. I could also go something like this, slowly come back down, something like that. So yeah. What are some other, again, we should be squeezing all the juice out of all the knowledge that we have. We know what the function 1 over x looks like because we had done it before. We also know that the limit doesn't exist at x equals 0, which again was on assignment 8. Oh no, it was a similar question to it, so it wasn't, sorry. But we've done that example before, 1 over x. So we have our 1 over x, something like that, something like this. Well, there's our function, 1 over x. Now, again, from our previous lectures, we knew that the limit as x goes to 0 of f of x. Mr. Walker has said, what about the case where a line crosses the limit, but approaches the limit from the top on one side and from the bottom of the other? Yeah, You can have that. I think if I was to draw that, you could have something very similar. You know, that's acceptable. So for kind of using that case, I could have it cross this line here, this this horizontal asymptote, and approach it, and then I could actually have it kind of approach here. So it doesn't have to cross it, but it's looking at the long-term behavior. It has to be approaching it, approaching that line. Now again, that approach could be on one side or the other. But that's a good question. I hope that answered it. I hope that was the meaning of the question. That's, if not, throw a clarification in the chat. We knew that that does not exist. However, we do know from the left-hand side it's equal to minus infinity and, oh, perfect. Good. So what does that mean? Well, graphically, that means that we have x equals 0 is a vertical asymptote. And the other thing to note that 1 over x, as it's getting really, really big, so again, going on this side, we'll say that the limit as x goes to infinity from the positive side of 1 over x, that's equal to 0. And we had done that previously before because we had dealt with limits of infinity. And on the other side, we have minus infinity 1 over x is equal to 0. Now, again, very similar to what we know now, we have a line here of y equals 0. And we showed now that y equals 0 is a horizontal asymptote. Now let's say, for instance, that we don't have a graph of it, because again, that's kind of how I showed you there, how to do that one. Let's go with, this is page 5. So we had shown that, okay, so first of all, here's a little tidbit. If r is a positive rational number, then the limit of this function 1 over x to the r, so for any positive r, positive rational r, that is 0. And similarly, if r is a positive rational number, then, oh, and I have one more condition, and that function xr is defined for all x, then that limit as x goes to minus infinity of the reciprocal is equal to 0. Okay. So here's our example. We're going to ask to evaluate the limit as x goes to infinity of 4x squared minus x plus 2 all over 6x squared plus 5x plus 1. So the idea here is, first, we're going to divide the numerator and the denominator by the highest power of x. And in this case, the highest power, not an ultimate power, but the highest power, again, we're not getting meta here, that it's the x squared. So I'm going to divide by the top the numerator as well as the denominator by x squared. So I have 4x squared divided by x squared, so that's just 4, minus I have x divided by x squared, so that's just 1 over x, plus 2 over x squared, all over, and then I have here in the denominator, I have 6, so I have 6x squared divided by x squared, so that's x squared divided by x, so that's just x to the 0, or just 1, plus I have 5, x divided by x squared gives me 5 over x, plus 1 over x squared. And now I can actually just kind of apply my limit rules. So here I have I could write these all out. One over x plus the limit. I'm going to move this 2 out in front here. So the limit as x squared goes to x goes to infinity of 1 over x squared all over 6 plus. Okay, yeah. So I can also apply the limit there. So what have I done? I've applied the sum rule of limits. I'm going to put the 5 out front here. So again, what this had told us at the beginning here is that 1 over x is equal to 0, 1 over x squared is equal to 0 as the limit of x goes to infinity. So that means here, this is going to go to 4, this is going to 0, this is going to 0 as well. Here I have, this is going to 6, this is going to 0, and this is going to 0. So I have 4 minus 0 plus 0, and then I have 6, 0 plus 0. So I'm left with 4 over 6. And simplifying that, I have just 2 over 3. So therefore, x equals 2/3 is a horizontal. Asymptote of that function. Okay, so is everyone okay with that so far? I think that's a good place to stop. I have one more example, but I think we'll cover that tomorrow's lecture. Again, we have a quiz tomorrow, so please finish the homework. I've posted solutions as well for it. If there are any errors or typos in it, which is possible, and again, it was a lot of typing. So again, if you see anything that could be a typo or an error, please send me an email at my RMC account. Again, or if you have any questions or if you're stuck on a problem, feel free to send me an email and I'll do my best to respond as soon as I can. So is there any questions before we sign off for today? Of course, I have to just give it a second to make sure if there's a 30-second delay. Excellent. All right. Yes. Okay. I will see everyone tomorrow, and we have our quiz at 3:40. So again, 15 minutes, and it'll be based on our assignment. Thank you, everyone, and have a good night.